will go to the fifth and last lecture of week 5 of this course, and in this lecture I will summarize everything that you learnt in week 5 and do a couple of practice problems. So, week 5 lecture 5 will be summary of week 5 and practice problems. In this week we learnt about mainly about point groups and space groups, but first we looked at the crystal systems and we said what are symmetry groups and what are the properties of groups. So, we defined these things called groups, okay, which have certain properties, and then we talked about the symmetry based classification of crystals and the essential symmetry of the crystal systems. So, what are the essential symmetries that are required to put crystals in different crystal systems. Then we discussed in detail about the point groups and about the space groups. And one of the things is that some of these things, identifying all the symmetry operations necessary to classify crystals into point groups and space groups, it is not always very easy. Okay. And so I mentioned that it is not very easy to visualize, and I recommend looking at some websites. So, there are some crystal symmetries on this website. This is the TU Grad's website, okay. And also there are the full detailed high resolution space groups which are available on this website. Okay. This is actually in a lot of detail, and we will probably it is good to know that these websites, this second website exists, and probably you will use it more after week 6 of this course. But definitely the crystal symmetries, there are some crystal symmetries that are there. This is actually a course on solid state, and in that there are some links to crystal structures. And actually the nice thing is that not only have they shown the crystal structures like FCC, diamond, zinc blende and so on, but they have also described all the symmetry operations both in the space group. So all the symmetry operations of the space group are described here. Now, let me do a couple of practice problems. Okay. See, one of the things you learnt in this week was how to transform an arbitrary point due to some symmetry operation. Okay. So, this question will test just your mathematical ability on how you can do this transformation due to a symmetry operation. So, the question is, how does a 4 under subscript 1 screw rotation about an axis perpendicular to the xy plane and passing through the point 1,4,0,0 transform an arbitrary point x, y, z. Okay. So, just to set up the problem, what you have is you have these axes. Okay, if you call this x, y and z axis. Okay, and you have an axis perpendicular to the xy plane and passing through the point 1,4,0,0. So, 1,4,4,0,0 is some point somewhere here, and you imagine that you have an axis like this. Okay, and it goes below the xy plane. So, this axis, and now you are doing a screw rotation about this axis. So what you are doing is a rotation. So, a 4-1 screw okay. So, this means rotation by 360 degrees divided by 4 equal to 90 degrees plus translation by 1/4. Okay. So what you have to do is you have to take a point, rotate it by 90 degrees, okay, but the rotation is about this axis that is shifted from the origin, and then translation by 1/4. Okay. So, now let us look at an arbitrary point. So, if you have an arbitrary point, okay, that will have coordinates x, y, z, okay, and let us look first at rotation by 90 degrees. First consider rotation by 90 degrees. Okay. Now, what is important is that this rotation is about this axis. So now suppose you had just the rotation about the z axis by 90 degrees, then you know how to do the transformation. Okay. So, but now you have a rotation about a different axis. Okay. So, now this axis is again parallel to the z axis. So first thing you note is that z coordinate does not change during rotation. Okay, so only the x y coordinates change, and so you can look at this this in terms in the x y plane. So if you just look at the rotation in the x y plane, okay, so in the x and y plane, and now this axis of rotation is located here at a distance of 1/4. Okay, so this axis is perpendicular to the xy plane in the along parallel to the z axis. An arbitrary point. Okay, if you look at an arbitrary point, okay, let us say I will take an arbitrary point right here. Its coordinate is x, y. We are not bothering about the z coordinate because the z coordinate is not changing. So we are just looking at its x and y coordinates, and now we are rotating about this point. Okay, so now with respect to this point, okay, if you can imagine that you are just you can imagine just shifting this y axis, so it comes here. Okay, and if you imagine it, if you imagine shifting this y axis here, and now you can think of this rotation about, you can think of rotation of this vector. Okay, and if you rotate it by 90 degrees, it will point, you can see that it will point somewhere here. And you will have the new x and y coordinates. So, this will give you the new x prime, y prime, okay. And you have to identify what this new x prime and y prime are in terms of x and y, and this is 90 degrees. This rotation is by 90 degrees. Okay. So, now how do you go about doing this? Okay. So if this were the origin, if this point that we are looking at was the origin of your system, okay, this point in particular was the origin of your system. I will call this point P. Okay. So the coordinate of this vector, okay, given, so from P to this point R, which is x y. Okay, so I am calling this O as the origin, P as this point where the where the axis of rotation, where the screw axis intersects the xy plane, and R as the point xy. So, now the vector from P to R, this vector, okay, this corresponds to x minus 1 by 4 and y. Okay, y is the y coordinate. Okay, the y coordinate is the same as it were if it were with respect to the origin O. Okay, only the x coordinate is shifted by 1 by 4. Okay, and now what you can imagine is, you can imagine doing a rotation of this point. Okay, if you imagine rotating this point, okay, so you can think of rotating this about the z axis by 90 degrees. So, if you do this rotation, then what you will get is, you will get the coordinates of the new point. Okay, so the coordinates of the new point, okay, will be given by rotation of x minus 1 by 4 by 90 degrees and y by 90 degrees. Now, notice that this PR is like the coordinate of x y with respect to P as the origin, and we are doing a rotation about the z axis for a coordinate system where P is the origin. Okay. So, let's redraw this in a slightly different way. So, what we will say is that you have a so this is the modified coordinate system, and now you have your origin at P, and you have this coordinate in this modified coordinate. Your coordinate of R is x minus 1 by 4 and y, and what you are doing is doing a 90 degree rotation in this coordinate system. So, you will get some new coordinates that look like this. So, after 90 degrees you will get some new coordinates. Okay. And in this coordinate system, okay, let me call these coordinates x double prime, y double prime. Okay, I will just call them x double prime, y double prime. They are in this coordinate system where the origin is at 1/4, at x equal to 1/4, y equal to 0, z equal to 0. So you can immediately write that x double prime is equal to x minus 1 by 4, that is the original coordinate, multiplied by cosine of theta, theta is 90 degrees. So, cosine of 90 degrees minus y, which is the y coordinate, times sine of 90 degrees. This equal to, so cosine of 90 degrees is 0. So, this will just give you, and sine of 90 degrees is 1. So, this will just give you minus y. Similarly, y double prime is equal to x minus 1 by 4 times sine of 90 degrees plus y cos of 90 degrees, okay, and this is just equal to x minus 1 by 4. So, now you have these coordinates, okay, but these are coordinates where the origin is actually shifted. Okay. So, if you go back to your coordinate, if you go back to the earlier to the actual coordinate system where you had this as the origin, O as the origin. Okay. Now, if you go back to that coordinate system, okay, then you know that the x coordinate, the x coordinate should be, is actually shifted back by 1 by 4. Okay. So what you will get is that in the coordinate system at O, okay, so the x prime y prime, okay, which was in the correct coordinate system. Okay. So, this is nothing but x double prime plus 1 by 4 y double prime. Okay. Now, the plus sign is because you shifted this with respect to p, this O is shifted back by 1 by 4. So, the x coordinate will be increased by 1 by 4. Okay. So, this new coordinate is nothing but minus y plus 1 by 4 and x minus 1 by 4. Okay. So, this is the effect of the rotation part of the screw operation. Okay. So, if we go back, what we wanted to do was we want to take an arbitrary point x, y, z, and we wanted to consider the effect of rotation. Okay, I will just mention that I call this x. The actual coordinate of this new point is x prime y prime. Okay, but in this new coordinate system that is centered at p, we call it x double prime y double prime. Okay, and we just use that tool just to get the final new coordinate. So, we started with the point x y and you end up with a point minus y plus 1 by 4 x minus 1 by 4 due to rotation by 90 degrees about this axis that is passing through p. Okay. So, this was the rotation part of the screw operation. Now, the next thing is a translation by 1 by 4th along the z axis. So, what you will get after the translation, so translation by 1 by 4th along z axis. Okay. So, we had our initial point was x y z that had the z coordinate of z. So, the new point, so it will give you the final coordinate. Okay. So, you have to take the coordinate after the screw operation. Okay. So, after we did the screw operation, these were the coordinates. This was the new x coordinate, this was the new y coordinate. Okay. And now the z coordinate, we said that the rotation part did not really change the z coordinate. So, the z coordinate was what it was before, but now after the translation you will get a new z coordinate. So, I will keep the x and y coordinate due to the rotation, but the new z coordinate will be shifted up due to translation. So, you are translating by 1 by 4th. So, this is the new z coordinate. Okay. So, let us go back to our figure. So, we took this point, rotated about this axis by 90 degrees, and then you shifted it up by 1 by 4th. Okay. So, we took this point, rotated about this axis by 90 degrees and then translated it up by 1/4. So, and that new point will have these coordinates. So, from x, y, z you went to minus y plus 1 by 4, x minus 1 by 4, z plus 1 by 4. So, this just goes to show that you can take any axis and you can find out translation of an arbitrary point, and this is actually extremely useful to read lot of the crystallographic tables. So, some of the websites that I showed, they talk about translation of an arbitrary point. Okay, and then you can use this to follow that. Okay. The next problem that I will briefly discuss now is the following. So, consider the zinc blende structure, which is closely related to the diamond lattice, but with different atoms at the face centers and the body diagonals. So, this is your diamond cubic structure, and if these blue and green atoms are the same, it is a diamond cubic structure. If they are different, if the green atoms are different from the blue atoms, okay, then it is called a zinc blende structure. Given that the order of the point group and the space group of diamond are 48 and 192. So, if you take a diamond cubic structure, not a zinc blende structure, if you take a diamond cubic structure, the order of the point group is 48 and the order of the space group is 192. And now I am asking the question, what are the possible values for order of space group of zinc blend? Okay. So, what can you infer from this about the order of the space group of zinc blend? Okay. Now, the first point, okay, now this is more an exercise in reasoning. So, the first point you note is that zinc blend structure has lower symmetry than diamond. Okay, so first thing is it has lower symmetry than diamond, in the sense that because these atoms were different, okay, all the symmetries of diamond that involved exchanging of these atoms will be absent in zinc blend. So, diamond is more symmetric, because in diamond diamond will have all the symmetries of zinc blend and some additional symmetries which are because this atom, the green and blue atoms, are the same. So, the next point is that all symmetries of zinc blend are present in diamond. Okay, so all the symmetries of zinc blend are actually present in diamond. Okay, so diamond has all the symmetries that zinc blend has. So, diamond contains all the symmetries of zinc blend. Of course, zinc blend does not contain all the symmetries of diamond. So, therefore, you can immediately say that the order of point group of zinc blend ZB, okay, ZB for zinc blend, okay, divides 48. So, the symmetry elements of zinc blend will form a subgroup of the point group of diamond. Okay, so the order of the point group of zinc blend divides 48, and you can say order of space group of zinc blend, this will divide 192, divides 192. Okay, so since it is a subgroup of the diamond structure, okay, so its orders will divide both the point group and space group orders will divide 48 and 192. Okay. Now, you can see that there are some symmetries in the zinc blend structure. So, for example, the zinc blend structure has the threefold axis that passes through the body diagonals. So, it has the four threefold axis of diamond. Okay, so these are present in the zinc blend structure. Okay, so you can clearly see that there are quite a few symmetries that are present. Similarly, this roto inversion axis, okay, fourfold roto inversion axis will also be present in zinc blend. It will also be a roto inversion axis for zinc blend. Okay, and let's draw the planar representation of zinc blend. Okay, so the planar representation of zinc blend will look like this. So, this is at z equal to 0, and then you have at z equal to 1/4, you will have, I will show it in a slightly different shape and size, just to emphasize that it is a sulfur. Then at z equal to half, you have, so So, this is at 1 by 4. At z equal to half, you will have the atoms at the phase centers that are located here. These are so this is half. At z equal to 3 by 4, you will have some more atoms here, which will again be the same as these atoms that are at 1 by 4. These are at 3 by 4. Okay. Now, you can immediately see that the diagonal mirrors are also there. This immediately tells you that the diagonal mirrors, okay, this will still be a mirror plane. The diagonal mirrors of the diamond structure are still mirrors in the zinc blende structure. Okay. So, clearly it has the 4 3-fold axis and it has the diagonal mirrors, okay, and you can immediately see that there are at least 6 mirrors, okay, if not more. So, and the 4 3-fold axis will generate another 8 operations. Okay. So, you already have 6 plus 8 14 operations that you have already generated from these just looking at mirrors. So, we clearly see that there are at least 6 mirrors and 4 3-fold rotations. Okay, and the 4 3-fold rotations, this 4 3-fold rotations will give you so each 3-fold rotation will generate 2 operations. Okay, it will be rotation by 120 degrees and rotation by 240 degrees. Okay, so you have 8 operations. So, at least 14 operations. Okay. Now you can also see that there are roto inversion axis, okay, 14 operations, and then you have roto inversion axis. This will be passing through the center of this. It will be perpendicular to the plane and passing through this center. Okay, that is a 4-fold roto inversion axis, and you have at least 3 roto inversion axis. Okay, perpendicular, one perpendicular to xy plane, one perpendicular to yz, and one perpendicular to xz plane. Okay, so this each roto inversion, each 4-fold, so 3 4 bars. Okay, now a 4-fold roto inversion axis will generate another 9 operations. So 4-fold roto inversion axis will generate 3, and you have 3 of them. So you have another 9 operations. Okay, some of these will be redundant. Okay, so but in any case you will definitely generate 3 C2s, 3 C2 axis due to this, or 3 2 axis. Okay. The point is that you will get at least 17 operations and probably a lot more. Okay. And now you can go back to this number. Okay. So, we said the order of the point group of zinc blende has to divide 48. Okay. And you can see that this implies that order of point group, okay, if it has to divide 48, now 48 divided by 2 equal to 24. Okay. 48 divided by 3 is equal to 16, and we already saw that we have more than 16 operations. Okay, so this is not possible. Okay, so 48 divided by 316 is not possible, since we counted at least 17 operations. So the order of the point group is actually 24. Okay, and it has to be 24 because it cannot be 48, and it has to divide 48. So it has to be and it is at least 17. So it has to be 24. Okay, so now what about the order of the space group? Okay, so now the order of the space group has to be a divisor of 192. It has to be a multiple of 24. Okay, has to be a multiple of 24 and has to be a divisor of 192. Okay, so it can be 24, 48 or 92. Okay, because these are the only three quantities which are multiples of 24 and divisors of 96. Okay, so these have to divide it has to divide 192. Okay, now again you can easily see that there are lot of screw axes that are there in zinc blende. Okay, so we can directly rule out 24. Okay, so 24 can be ruled out because there are additional operations. So 24 can be ruled out because there are additional operations beyond the point group. Okay, so 24 is ruled out. Okay, because 24 is the order of the point group, and the space group has more than 24 operations, definitely, because it has screw operations, and then you can also get symmetries by extending the cell. Okay, now so it can be either 48 or 96. Okay, and at this point, unless you work it out, you cannot tell whether it is 48 or 96. Okay, so but the correct answer is 192. So unless you work out, you cannot tell whether it is 48 or 96. Okay, but the correct answer is 96. Okay, and this cannot be unless you need to work out. Okay, so this needs to be worked out. Okay, but again there are ways to see why it has to be greater than 48. Just as we showed that the order of the point group has to be greater than 17. Okay, we can show that the order of the space group will be greater than 48, and the correct answer is 96. Okay, so with this I will conclude this problem, and I will conclude the lectures of week 5 of this course. Okay, and the next lecture we will start week 6 of this course. Thank you.